Hi everyone, very good afternoon. Welcome to the week 5 doubt clearing session for aluminium based alloys and metal matrix composites. I am Ananya Nath. I am a PhD student at IIT Delhi. So let's start today's session. We ended up with a few query about week 4, and we'll have a small recap on week 3 4 on the strain hardening part of the heat treatable alloys. Then we'll jump into the week 5 topics. Those are basically the strain hardening process for non-heat treatable alloys, and then we'll start our new topic of the week 5 lecture 4 and 5, which is mostly recovery and recrystallization. So before that, and also apart from that, we'll discuss about the current semester week 3 week 4 MCQs and the week 5 MCQ for the previous semester. If you have any doubt, you can directly ask me, or else I'll start with my PPT. Any specific doubt? No?
No, ma'am.
Okay. So we'll start with the PPT. First of all, let's have a recap on the strain hardening part for heat treatable alloys. We have seen that for heat treatable alloys, we were heating the material, then we were cooling down, and based upon the cooling rate, we were getting the grain sizes. So for fast cooling, the grain size is generally smaller. For slow cooling, the grain size is generally bigger, because for slow cooling, the grains get enough time to grow and nucleate. So this is why the grain size are generally bigger. For heat treatable alloys, what does it mean is the aluminium alloys which can be heat treated, means the heating and cooling, the different stages of heating, then different stages of cooling, and also another very important topic, which is aging, can give us the result of strain hardening, means thus just we are just increasing the hardness or strength of the material, because aluminiums are ideally known for its ductility. So aluminium and its alloys are ductile in nature, so we are just increasing the hardness or strength of that particular alloy. But there are 8 to 9 different grades. There are wrought alloys, cast alloys of different 1000 series and 100 series. And those, some of them are heat treatable, some of them are not heat treatable. So for heat treatable alloys, we can just heat up it or increase the temperature, hold it for certain time, then cool it down, then do the aging, loading, reloading, these things, and we can increase the hardness. But for non-heat treatable alloys, what does it mean is we can do these things, but those alloys will not really act differently. Like, those alloys will not get that much hardness or increase in hardness if we do the heat treatment. This is why those are called non-heat treatable. So for them, we take help of other processes by which we can increase their strength. So one of those processes is cold working. Cold working comes with different processes again, like stretching, drawing, then extrusion, then just normal forming or forging process. So these are basically the cold working processes. If we increase the temperature, it will be called as hot working. But ideally, temperature doesn't make any difference in the non-heat treatable alloys. This is why we typically use cold working techniques to increase their hardness. So let's see from lecture 1 to lecture 5 what were the topics discussed. So first was the heat treatable 700 series alloy, which is basically which was 7075. So and another was 7005. So for these two alloys, T6 and T7 conditions are used to increase their strength. We know for 7000 series there will be GP zones, then there will be eta, like the phases
Ma'am,
eta prime. Yes.
are you also changing the slides or it's just
No,
the
no,
strain height?
I'm not changing the slides. I'm
Okay.
just telling you about it.
Yeah, yeah. Ma'am, like one more doubt, does 8x series also comes under precipitation hardenable series?
Yes, 8x is 800 series is or 8000 series is a hardenable, precipitation hardenable. There are
Okay, ma'am, in many of the books I have seen only till like they are counting 2, 6, and 7, like they are not including 8.
Yes. So basically what happens is this 6 and 7000 series are the most widely used aluminum alloys. You can find their application in every sector really. Like from automobile to aerospace, the 2000 series, 7000 and 6000. But for 8000 series, what happens is those are precipitate hardenable, but there are no such very prominent sequence of precipitations like GP zone, then the gamma or delta prime and delta. So we can directly achieve the precipitations. So the sequence are not really discussed in every books or sites or just websites, because those are not prominent for 8000 series. And you'll also see for 8000 series in different sequence we get different types of precipitations. So among the precipitations also, some arrangement in between them, some compound formation and bonding debonding is happening. So 8000 series is a heat treatable alloy, but it has some applications in some sectors, but it's not that much popular as the 6000 and 7000 are. So yeah, so in first lecture, the 7000 series and 8000 was discussed. So as I said, for 8000, lithium is the alloying element, and for lithium, this 8000 series is called the lightest alloy among all other aluminium alloys. So for the highest second phase precipitate, which is Al3 Li, we are getting, which has the L12 shape. So this is basically the L12 shape. Right. This is the L12. It's basically a face-centered atom or face-centered crystal structure where this this is these are the lithium and these are the aluminum. So it's basically same. Wherever you are placing for L12, it will look like it will look similar wherever you place the lithium or aluminum. And
Excuse me, ma'am.
yes.
Ma'am, actually, I did not understand this L12 and sir was
Oh,
discussing about
okay.
this
So
structures.
it's very simple. So there are a type of symmetry, which is another topic in crystal structure. If you go for the crystal structure only, so there are four primitive lattices: FCC, BCC, HCP, and normal cubic structure. But if you go for the next step, then there are 14 crystal structures. These are unit cells, 4 unit cells, then 14 crystal structure, which includes the trigonal, tetragonal, normal cubic, rhombohedral, those kind of things. And the combination of 4 unit cell and all this crystals make the 14 breve lattice. So in after breve lattice, there is another topic which is the symmetry. So there are different types of symmetries in different crystal structures. So there are one thing is one fold, two fold, three fold, fold symmetry. So according to those things, this L12, L1, L01, L22, these things are known. So you have to go for that nomenclature and the fold symmetry part if you want to know about this L12. Otherwise, it's a simple FCC. But in FCC also, how the atoms are arranged, in what position, which type of atoms are present. Based upon that, these names are given.
Ma'am, that means L12 is like two-fold symmetry or something.
Yes, yes. So it's a normal FCC where in the faces, the lithium, I think in the faces, aluminum alloys are there, aluminum atoms, and in the corners, lithium, or vice versa. I need to see, but it's normal. Whatever we see in
Okay, ma'am.
normal FCC structures, that way only. And for the next one, for 8000 series, one was the gamma or delta phase. We were getting aluminum lithium only 1:1 ratio. There the structure was a bit different. There, along with the corners and faces, atoms were present in the edges as well. So the structure somewhat looks like this. And along this atoms are lithium, okay, and apart from that, aluminiums were present in the edges. So this is the aluminum is to lithium 1:1 ratio, which is called B32. So it's also a type of lattice. It also follows another type of symmetry and its characteristics. This is why it's called B32. So apart from that, for the strengthening, so these were the topics, the natural aging and artificial aging. So if we are doing it in room temperature, it will be called natural aging. Otherwise, for elevated temperature, it will be called artificial aging. In artificial aging, the yield point will come up soon than natural aging. The in natural aging, it will take longer time to get etched and to get the maximum or high strength. This is why the formation of GP zone is more or less homogeneous. Then the formation of the sequence of GP, then theta, theta prime, theta double prime, theta prime, theta. These things were prominent, but at the same time, it was taking longer time to get that strength. So that is why for artificial aging, we get the peak hardness. Then after that, as I said, homogeneous GP zone formation was very important for us. Then the precipitates were formed at the last stage, but even after, if we continue doing the aging, then we'll have a over aged material, which is nothing but the precipitations were sitting like this, but after over aging, all the precipitations adjacent to them will get attached, and the size of the precipitate will continue growing, and as a result the distance between this will increase, and as a result the dislocations will again feel free or easy to move through the solute atoms or precipitates. So they can again move very easily inside the lattice. This is why for overaging, the strain hardening amount were decreasing and the ductility will increase. So based upon our application, we use the different types of heat treatments, because it's not like uh, if we okay it's not like if we want if we are going for hardening, some kind of hardening, we'll always go for the peak hardness. No, there are a lot of variation in hardening also. There are T1 to T8, 9, 10 types of hardening. We often go for overaging as well to get a less amount of hardness than peak hardness. So it all depends upon the application we were using the aluminum alloys. So then the dislocation density was another topic. So in aging, we were just restricting the dislocation motions, but we were not that much concerned about the dislocation density. because in heat treatable alloy, anyhow, by increasing the temperature or strain rate, we can handle or we can uh, control the dislocation and the solid atoms movement. We can make the precipitates form, and this is why we were not concerned on this dislocation density. But for non-heat treatable alloys, we have to be very concerned about the dislocation density, because that is the one thing using which we can get rid of this problem of non-heat treatable alloys, because there are two things inside the lattice: solute atoms and the dislocation. So we have to play with these two things inside the lattice to increase the strength or increase the ductility, any one of this. So this is why for non-heat treatable alloys we go for increasing the dislocation density. This is why, this is what we have seen in the whole lecture series of week 5. So we do cold working like forging, extrusion, deep drawing or forming. This processes basically at room temperature, or a bit more temperature we apply sometimes, but mostly it's at room temperature. So this is why it's called cold working, and this is how by cold working the grains are stretched, and this is why the dislocation density increases very much when we try to go for, when we are doing the cold working, as the grains are stretched. So inside the lattice geometry, the atoms, the solutes, dislocations don't get enough time to flow with that cold working, because the rate of cold working is high typically. So what happens is, due to the less time for the grains to get arranged properly, or the lattices, solute and dislocations, the lattices uh, make or some new set of dislocations are appeared. So this is why the density increases, and also to accommodate a lot of strain inside the material, we need to, or the lattice needs to move the dislocations. But it also at the same time, we are not giving that much enough time to grow properly for the, or we are not giving enough time to the dislocations to grow properly. This is why a new set of dislocations form, and to accommodate the strain, this also happens. And as a lot of dislocations, new dislocations have formed, the new dislocations and the old dislocations start interacting with themselves, and start interfering with themselves, and as a result they themselves restrict their own movement. So dislocations pile up happens, polygonization happens. So let's see what are the other topics. So before that, there were nomenclature for the cold working strengthening as well. If it's as fabricated, no, nothing has is applied. So it's, we call, or we use the nomenclature F. Then if it's annealed and recrystallized, so it's O. Then if we have done the strain hardening, and so it's like H1, but under H1 also there are H1 to 14, 16, 18. So 8 means the fully hardened, or 75% or 80% reduction has done to the cross section, and the lowest strain hardened by using cold working is the H12, which gives us 20% reduction in the cross section. So we are stretching the material. So if we are stretching the material by this, so it will be stretched like the cross section of this geometry will decrease. So this is why the reduction in cross section, depending upon the reduction in cross section, we give the nomenclature like H1, 2, 1, 4, 1, 6, 1, 8. Then yeah, and the second digit in this tells us about the level and degree of strain hardening in that particular cold work material. Then the next one was H19. So 19 is yes, extra hardened, or it's similar to overaging in case of our heat treatable alloys. So we are going beyond the peak thing, peak hardness. It's extra hardened, and then decrease the hardness again, we go for reduction in the hardness. So we basically go for the ductility increase processes like annealing, and these things were, yeah, up to this point. There are H332 also, but those are similar things like the nomenclatures. So let's discuss about the main thing, which is the dislocation density. So as I said, for cold working, the dislocation density has increased, and this is why they will themselves act as a barrier or restriction towards their movement inside the lattice. So for a particular lattice, there are some slip systems. I have mentioned in my first class also. So in the slip system, the Berger vector, these things are mainly responsible, or these things are the main thing if we are talking about dislocation and their movement, because towards the slip direction and through the slip system or slip planes, the dislocations really move. So every lattices have their own slip system, means a particular and specific slip plane and slip direction, and at that direct or towards that direction only and through that plane only the dislocations move, otherwise they do not move. So as for substitutional solute atoms, the solute atoms need to have the nearby vacancy to jump into that also after having a certain level of activation energy. Similarly, for dislocations also, dislocations can easily move because there are a lot of slip systems. But if the material or lattice is not having that much slip system, then the dislocations will also face difficulty to move forward. So for FCC, it has a direction of 111, which is having the slip system. So if the dislocation is facing that particular direction, then only it will move. But you can imagine if this is a particular FCC, and just imagine that this is the slip plane and this will be the slip direction. So the whole lattice is made up of this type of things only, na? So there will be a lot of atoms or a lot of lattices, and all the lattices will have this type of plane. So this is why dislocations do have plenty of that slip systems or slip planes inside a particular lattice. Also, in a particular unit cell also, sometimes lattices have multiple slip system in one lattice or one unit cell. For that case, in that case, the dislocations find more than enough places to go or to move forward. This is why the movement of dislocations is easier than the movement of solute atoms.
Excuse me, ma'am.
Yes.
Ma'am, there is one question here. Let's suppose if solute atom is shared by the dislocations,
Hmm.
take example of 8 series alloys.
Huh.
So the surface energy increases, right?
Yes.
Because we have the more surface area that is exposed to
Yes.
dislocation.
Yes.
So at this case, why ductility decreases? I mean,
Okay.
it should
So
increase.
okay. So that means, so why we use the solute atoms? If this is the solute atoms, we use this solute atoms or atom to restrict the movement of the dislocation. If this is the dislocation and it's moving towards this solute atom, it's moving very freely everywhere. But as soon as it comes or meet the solute atoms or precipitates, it will stop. It has to stop its movement, because to overcome or jump through this solute or precipitate, it needs more activation energy. And anyhow, at the time of jumping off or breaking the barrier of the solute, If somehow this solute sheared and gets halved by the movement of dislocation, the surface area increases. That means in layman term, if you try to understand, this dislocation now have to have much more activation energy to overcome the whole surface area. That gives us the surface energy. So now the dislocations cannot move, and the ductility is something which is defined by the dislocation movement. Ductility means if this is a sample, I am pulling it from two sides, and if the strain is happening inside it, now the length is this increased length, means the dislocations have moved inside the material to accommodate that strain. This is why if the dislocation movement is hindered by somehow, means the ductility is not what is we are getting, means we are not getting any ductility result, or the result of that test is not showing us that ductility of the material, means the material is hardened, the material is harder. This is why we cannot, or the material cannot sustain much more strain or to accommodate much more strain inside the lattice. Is it okay?
Accommodation of the strain means what do you mean to say?
Okay,
Uh,
so accommodation means just one one minute. So I have a sample of this, okay, and I'm pulling it from both the sides. Means I am giving some strain, or I am applying a force of F. So the result will be this after some time. If it's a ductile material, means some strain is happening. Strain is nothing but percentage elongation, na? The deformed versus by
yes.
the original length.
All right.
So
Yes.
if the material is ductile, then only it is possible. If the material is not ductile, then what will happen? After some time, there will be a breakage in the material, right? It it will try to get the strain or percentage elongation for some times, but after some time it will break. But for ductile material, it will have much more strain than a brittle material. That is the difference between the ductile and the brittle material. Up to this point we know that. So we are having some strain in the material. From outside we can see the strain, but what is happening in the inside? This is what I am trying to explain. So inside what happens, there are grains, there are multiple grains inside a particular material. These grains are not this much bigger. Those are small microscopic grains. These grains will try to stretch themselves. So inside a particular grain, there are lattice structures. They cannot stretch beyond a particular percentage. So what happens is there will be mismatch, or there will be some dislocations, some newborn dislocations. If these are the atoms inside it, due to the stretching, there will be breaking of bonds in the atom, and some extra half plane will appear. This is what the dislocation means. This dislocation, now this is one dislocation, and when we are pulling it from both the sides, there will be a lot of dislocations uh, forming inside the material, and these dislocations are moving inside the lattice to accommodate the strain, means to give rise that percentage elongation.
Understood, ma'am. Right.
Okay.
Ma'am, one another question. Actually, sir said in the lecture, like if we are using the two digits, if we are using H for non-heat
Yes.
treatable alloys, like 5 series,
Yes.
so the first letter indicates means like H1. So this indicates means alloy has been strain hardened, right?
Yes.
And the second letter indicates like 8 means 100% hardened and 4 means half hardened. But if there is three digits like 5083H321,
Hmm.
right? So the three indicates strain hardened first and stabilized and NA, right?
Hmm.
And the second digit indicates like we are just after the strain hardening remains after the stabilization. So this remains the second digits. And what about this third digit one? Like if we take the example 5083H321.
Where did you see this type of three-digit nomenclature?
Actually, ma'am, I am working with the alloy 5083H321. Actually, I am working. I am a research scholar in NIT Jalandhar, and I am working in aluminium alloy friction stir welding.
Okay,
So
okay.
I selected these alloys for means for my welding purpose to this
Okay, okay.
material. So it is 5083 capital H 321.
Okay, so Shailesh, I need to also see this thing. What does this third digit means? Because I also work with aluminium, but our team work with heat treatable alloys. There, this
Okay,
type of problems do not arise. So I need to see. I'll tell you in the next class for sure.
sure, ma'am. Actually, ma'am, in
Yes.
heat treatable alloys also we have three digits like 7075T651.
Okay, that
Yeah.
I didn't see those type of things yet. So
Okay.
yeah, no problem. I'll see this. I'll note
Sure.
it down.
Sure. Sure, ma'am. Sure. Thank you.
Hmm. 3 2 1. It's
Yes. Yes. 5083 H321, or there is one another alloy 5083 H triple one.
okay. Okay, I'll see. I'll see and tell you in the next class. Okay. So yeah, I was telling you about the dislocations. So yeah, till that point we have understood how we are accommodating the strain. What does it mean by this sentence of accommodating the strain? And our job is to harden the material means our job is to restrict the dislocation movement. So if the dislocation movement is resulting in the percentage elongation means is showing the ductility in the material, our job is to harden the material means decrease the ductility. So the ductility is the result of the dislocation movement. So this is why we are trying to restrict the dislocation movement anyhow. So we go for the alloying. We mix the solute atoms means the alloying elements which are called solute atoms because it's also a solid solution, and these are substitutional solutes. So how we are restricting the dislocation movement? This is how we do the hardening. So yeah, I was talking about lecture 2, I think, or lecture 3. Okay, so we'll start with the lecture 3 now. So yeah, so a lot of new dislocations have formed inside the material, and these new dislocations will be of two type. Obviously, there are only possible two types of dislocations mostly. One is edge, another is screw. So this both dislocations have their own characteristics, own properties, and their motion is different. Their Berger vectors are different. Their direction of movement and everything is different. So they both can interact with themselves. They both can interact with each other, like the screw can interact with screw, other screw, the edge can interact with other edge, the edge can interact with the screw dislocations, or this new set of dislocations or newly formed dislocations can interact with the old dislocations as well. So what happens is this barrier of the movement or the barrier in the movement of the dislocation is happening because of themselves only. So this is how really we do the hardening in the non-heat treatable alloys by forming new set of dislocations. Now previously the dislocations were moving so fast that the solute atoms couldn't catch up them until unless we increase the strain rate and those things. But now we have played a little bit different. We have increased the dislocation density in such a way that now they will feel different or they will feel difficult to move because of themselves only. So this type of interaction or the barrier is called the Lomer Cottrell barrier. It's also very important if you are dealing with some metallurgical works, this Cottrell barrier. Now, there are two types of dislocations. So the next slide is on the types of interaction and how they are feeling difficult to move. So we have been taught about the jogs and kins. So if this is if this is a edge dislocation, and through this slip plane the edge dislocation is moving in this direction. Now the dislocation will not change the slip plane until unless some external force is applied onto that particular dislocation, because to change the slip plane it needs to have some external load or externally applied force. Until unless it will move forward, but it will always be on a same slip plane, on a same slip system, means in a same slip plane and towards the same slip direction. Now what happened is, because of some externally applied load, or as we are going for cold working, the externally applied load is very large, and also we are not giving them enough time to rearrange or to move properly. So because of that, and also a new set of dislocations have formed inside the lattice, and they are interacting with each other. So due to that interaction also, there can be breakage in the dislocations. So it can happen like they have broken in 2 3 parts, and they have found other set of dislocations with opposite sign. So they will just tangle each other and there will be a continuous line. So the what we say is, no dislocation will be left there. But another thing what can happen is, they have interacted with each other, and now there is a breakage in the dislocation line, and now the two parts after breaking are going through two separate planes. Before, the dislocation was in plane 1, but right now after breakage the next part of the dislocation is moving in slip plane 2, and there is a length in how many planes they have got separated, or how many distance they have traveled due to the breakage, and this distance is p1, length in the dislocation break. And now as they have been broken in themselves, they will feel difficult to move further. And if this breakage has happened in two different plane, it will be called as jogs. And if even after breaking the dislocation still has remained in the same slip system, means same slip plane and direction, then it will be called as kink. It's as simple as it is. So there are a lot of example of jogs and kinks sir has demonstrated in the lecture 3. The interaction between two edge dislocations, interaction between screw and edge, then interaction between two screw. So the result will be in that way only. So there is a small equation I have given here. So the energy of dislocation, so there is a certain amount of energy which is associated with the dislocation when it's moving. It will always try to move from higher energy to lower energy side to get a stabilized and equilibrium position. Always all the atoms, electrons, everything try to go from higher to lower energy state through our energy gradient. So if the energy associated with that particular dislocation is equal to alpha g b1 b square, it's b1, it's the suffix is b1, then uh, this b1 will denote the length of the dislocation. So higher the b1, higher will be the energy. And also we want the dislocation to move towards the lower energy gradient, because after that only it will not move further. And also if it has arranged themselves in the low energy gradient site or lower energy site or lower energy configuration, it will not try to move further because it's now in at its stable position or equilibrium position. And also this breakage impede the motion of the dislocation. And as I said already, if the dislocation movement we have somehow hindered, means the ductility will decrease. We have done the hardening. The next topic which was taught,
Excuse me, ma'am.
yes.
Ma'am, could you please explain how this screw dislocation interact with edge dislocation with
Okay,
diagram?
okay, okay. So I'll take the example which was taken in the class in the lecture. Uh, so yeah, this is a plane. This is a slip plane. Slip plane means through this plane the dislocation will move. Now at which direction, that will indicate by the slip direction. So this both will form a slip system. So in this plane, now what does a plane means is, this is a lattice. If this is a face centered lattice, then all the face will have an atom middle at the middle position. So this is a plane. This is a plane. Okay, so this unit cell is having 6 planes. So in the similar manner, this is a plane, for example, which is having the slip system of that particular lattice. Now this plane is having one dislocation, means there is a gap or an extra half plane in that plane. This is the dislocation, and this dislocation is moving in this direction. Okay, or this dislocation is moving in this direction, whatever. So if there are two planes in which two dislocations are interacting with themselves, okay, so this is one plane and this is one plane. In this plane, the dislocation is moving in this direction, and in this plane the dislocation is moving in this direction. This is 1, this is 2, and because of the interaction of both the dislocations, and also at the same time we are applying a lot of load and force externally, this can happen that this plane or this dislocation is remained as it is, but the dislocation which was moving through this plane has now shifted by some length. The plane has not shifted, okay? The plane remains there, but the dislocation movement has been shifted to the next plane.
Oh, okay, right, understood. Right.
Okay. Yeah, I felt like you have, I think, misunderstood. So the plane has not shifted. The dislocation was moving in this plane. Now the breakage, after breaking, the other part of the dislocation has come down to this plane. And if this breakage, after breakage, this dislocation has come down to the next plane or anywhere other than the previous slip plane, then this will be called as jog. But if even after breaking, the dislocation remains at that plane only, but if there is a discontinuity or breaking in a particular dislocation, it will be called as kink. Okay. So similarly, we can see for edge dislocation we can have kinks, but for screw dislocation it's easy to have the kinks because the
Oh,
screw.
excuse me, ma'am.
Yes.
Ma'am, can you please explain kink again?
Okay. So for kinks, if this is one, just this is one screw dislocation. I have told you in previous class the screw dislocation moves like helical, so it will have a circular motion, and it will have the movement of the extra half plane, how the extra half plane is moving. So the direction will be denoted by Berger vector, and there is one edge dislocation which is moving towards this direction. This is B1, this is B2. So yeah, this is the symbol of dislocation. This is the symbol of mainly extra half plane. So then as a result, there is a breakage in both, somehow there is a breakage in both the what's it, dislocations. This is the edge This is the screw. So now you can see in the first one, the edge one, from this picture actually you cannot determine, because from this picture it looks like both the things have shifted by one plane, but it's actually not true, because for edge it has shifted by one plane. Before it was moving through this plane, but now it is moving through this plane. The plane is different now, so it will be called as jog. But for screw dislocation in a particular plane, this jog was this screw was moving. After the interaction, through this particular plane only the jog is moving, but the extra half plane now has broken down into two different parts. So there are now two extra half, and those are somehow connected through this line. Means there are atoms. Is it clear how the kinks are forming?
Mom, basically the plane remains the same.
Yes, yes. Okay.
Okay.
Anyhow, in any types of interaction, the plane will remain same. The dislocation has will be broken down. Okay. Anyhow, in jogs also, the plane will be same. As I said, na, if this is the plane, if this is the below plane, if this is the third plane, this is the fourth plane. Okay. The dislocation was moving through this plane, and now the dislocation has come down to this plane also. So there are two dislocations, not two dislocations, they are connected, but the dislocation has broken down from here. It has now formed this type of structure. The plane will not break down, plane will remain same, the dislocation has broken down.
Mom, actually, I mean that for kink, there is no jump in the plane. Like
Yes,
the
there is
dislocation
no
continues.
jump of the dislocation in another plane. It will remain in the same plane. But for
Yes,
jogs,
mom.
it will jump in the next plane. So some portion will be
Yes,
remain
mom.
in plane 1 and some portion will come to plane 2. This is the difference between jogs and kings. These are very
Uh,
important. Yes.
Ma'am, how this jog has formed in screw dislocation?
Uh, okay. So it depends upon the energy associated with the dislocations which are moving and also which are interacting. We cannot say that if the energy of the dislocation is higher, then only it will form jogs, because for jogs it needs to come down to another plane. It needs more energy. It's not like that. There is some energy associated with each dislocation, and if they need to they are jumping from one plane to another plane, they will need some more energy or some less energy. We can't say, because there is an interaction between two types of dislocations. For screw dislocation, the movement and the Berger vector both are similar, but for for edge dislocation, the movement or the slip direction or the direction of the movement of the dislocation and the Berger vector are perpendicular. So there are a lot of things related to both the dislocations, and they both are interacting with each other. So we cannot say how or why it's jogs and why it's kings, but these are the possibilities that can happen.
All right, ma'am.
Yeah.
Excuse
So
me, ma'am.
yes.
Ma'am, actually, in the lecture, we have discussed that in case of screw and edge dislocation interact, then we have a jog with the edge and a kink with the screw. These are the standard templates it always follows.
Like as in that particular example it was taught, like if two screws are moving, then both this screw dislocation will have jogs, and if it's interacting with
Yes.
edge it will have kink. It's not standard, but this is what generally happens because of the interaction. Means it's like the screw will always follow the parallel Berger vector direction. and the edge dislocation will always follow the perpendicular direction to the buzzer vector. So, and they both are interacting with each other. This is why generally has been found that if the edge is interacting with screw, then screw will have kink and the edge will have jog. But if the two edge are interacting with each other, it can happen only a jog has happened and no kinks has happened. It can happen that if a screw and edge has interacted with each other, only a breaking in the edge dislocation has happened, and there is no such breaking or no such interruption in the screw dislocation. It can happen.
Ma'am, so like, what is the parameter which decides this? Like, what will happen?
The deformation we are applying from outside, the number of dislocations which are present already and the number of dislocations which are kind of newborn. The as I said, क्या बोलते हैं उसको, the amount of deformation we are giving, the time in which we are giving the that much deformation, it's not that much
Okay,
defined,
ma'am.
because the dislocation movement is also an irregular thing. It's not uniform. It doesn't follow any rule that this is the rule. If there is two dislocation, one solid atoms, the solid atom will move like this and dislocation is moved like this, because neither the dislocation nor their direction is fixed, but neither the dislocation amount and their like concentration density is fixed. So you cannot decide exactly what will happen, but these are the possible cases which are found inside a particular aluminum alloy.
Yes, ma'am, I understand.
And it has been found that generally whenever there is a interaction between edge and screw, if both dislocation has encountered a breaking, then the edge will have the jog and the screw will have the kink. It's not like always they both will have the breaking. It can happen, it may happen that the screw will have the breaking and the edge will be as it is. So it depends upon many factors. And the factors which are really influencing is mainly the dislocation density, where the dislocations are present, how much is the density, and we cannot define that those things, or we cannot formulate those things. So yeah, this pile up of the dislocations are also called the forest dislocations, because these dislocations will now create a kind of clusters, and this is what the next topic was. So through the interaction of the dislocations themselves, they will lock each other. So we have seen one technique of strain hardening already, this jogs and kinks. So they are moving just like normally from their plates, but due to their own interaction, they are locking each other. They are making some restrictions in their own path of movement. So this is one type of strain hardening which is taking place inside the material, and as I have already said, that locking of the dislocation is our main motive. This is how we can strengthen a material. Doesn't matter it is heat treatable or not heat treatable, we have to somehow lock the dislocation movement. So yeah, the next type of strain hardening we can, or following which we can achieve the strain hardening, is the amount of cold working we are giving. So everywhere only the amount of cold working is the main thing, but whatever happening inside the material, we really don't have 100% or we cannot say that yes, if I do this much of cold working, then this much of dislocation will uh, formed. We cannot say it with, because this is not 100% truth. We can say that this is the cold working we are giving and this is the strength we are getting, but what is happening inside the lattice, We can see under microscope, but we cannot determine exactly 100% result. We cannot formulate or simulate. We can only see under microscope what is happening, and the possible things that mostly happen inside the lattice are this type of jogs, kings, then this forest dislocation, pile up of the dislocation, and then the next is cell structure. So what happens is, through the interaction of the dislocations, generally they lock each other, which is called the C's locks. So by penetrating each other, by interacting with each other, by breaking each other. So another thing is this cell structure. So when there is a lot of newborn dislocations, the dislocation density is very high inside the lattice, there will be pile up of the dislocation. So they always will try to have a low energy configuration among themselves so that they don't need to move. Because if this happens, like there are a lot of dislocation density, we have done a lot of cold working, and now the dislocations have not arranged themselves, so they are at a high energy configuration. They are having the energy associated with each dislocation is very high. Then the result will be a lot of residual stress inside the material. Residual stress means we are doing some or we are applying some external force, and we are having some percentage elongation, but due to strain hardening and due to other prospects, we are having a material now which is strain hardened, but uh, it's like the ductility is not that much right now, but the stress is remained inside the lattice, so which is called the residual stress. Okay, so the next phenomena is the cell structure. So this is why the dislocations always try to arrange themselves in such a way that they can have the low energy configuration, and they can arrange themselves in such a way that there is a minimum amount of residual stress remained inside the lattice. So cell structure is like the dislocations are piling up each other, like they are gathering at a place, and they are just forming kind of cell structure by gathering. I have a picture, I think. Yes. So this is a picture of the cell structure which are generally formed by the dislocations. You can see in microscopic scales also you cannot see the dislocation because it's a extra half plane. It's a extra half plane which is having few atoms, and interatomic distance you really cannot see under even microscope, but here you can see clearly the cell structures and the cell what say the cell boundaries. So what happens is the dislocation in density is so high that they have pile up, and now they have gained a cellular structure. So what was taught in the class, like inside the lattice, the dislocation density is so high that they have piled up like this, and they are trying to make some cellular structure so that they can have a low energy gradient and low energy configuration. This is the thing. Okay, this picture was demonstrated. So yeah, this is one phenomena, or this is one possible situation which really happens inside the material. When we apply the cold working, the deformation happening inside the material, but at the same time we are hardening the material. So you can think like in cold working we are stretching the material, so we are increasing the length, or there is a lot of percentage elongation inside the material which shows the ductility of a particular material, but still we are hardening the material. So it's such a nice phenomena by which we are getting some percentage elongation result. We are resulting with a ductility, but at the same time we are decreasing the ductility. with the result of ductility. So yeah, this piling up or arrangement of the dislocation depends upon the cold working I am giving. Also, the temperature plays an important role, because even if it is called cold working, but it's not really, it doesn't take place in a cold temperature. The temperature is typically room temperature or slight higher temperature, but not that much. So if we increase the temperature, obviously this thing will be happening easily and in a faster way. So pile up of dislocation happens at the grain boundaries, because those are the most energy gradient place, because all the fracture, all the piling up, these things happen in the grain boundaries only. And also, before cold working, in cold working we are stretching the grains, so the grain size will be stretched, but at the same time we are making it finer, because of this phenomena taking place inside the material. But if the grains are smaller, the number of grain boundary is more, and that in that case these things will be taking place easily, this piling up of dislocations, then this type of hardening for non-heat treatable alloys. So generally we start with the smaller grain only, because for larger grain these things will not take place that much easily, because the grain boundaries are lesser in number. So this is one thing. The next important thing is the cross slip. So cross slip is also important for this piling up. So for piling up, for heat treatable alloy, if you can remember, for heat treatable alloys, up to aging, if this was the curve, so up to the peak aging or peak hardness, the solute atoms were getting bonded with each other and were making the precipitates, unless until they get that equilibrium position. So they were trying to lower down the mismatch between their lattice and the parent lattice. They were trying to maintain the coherency or coherence in between them, means their lattice and the parent lattice, and at the same time they were trying to achieve the equilibrium. And when the equilibrium was achieved, it was peak hardened. And when we were going for again overaging, or we were keeping the material for longer time, then the precipitates continued growing, and they formed a bigger cluster, bigger precipitates, due to which the distance between them increased, that lambda increased, and due to which the dislocations got free path to move forward. Here, there the solute atom movement was important than the dislocation movement, because we were playing with the solute atoms to log the dislocation. But here, as we are doing the cold working, solute atoms are so small that it's one atom. How small it is, it's not even micro, it's nano scale thing. So we cannot play with the solute atoms in case of cold working, because we are not giving any heat to the solute atoms, and solute atoms are substitutional in case of aluminium. So they need to have a minimum activation energy, or externally provided temperature or something, to achieve or to overcome the barrier of the thermal or mechanical or activation barrier, activation energy, to find the nearby vacant place and jump into that. So this those that was tougher. But in this case, we cannot play with the solid atoms, because not at all we are providing any temperature. So we cannot anyhow misplace the solid atoms. Due to the cold working, there can be some alignment of the grains, some stretching of the grains of the solid atoms, but we cannot really play with the solid atoms. This is why we have taken help of the dislocation. So there we were trying to move the solute atoms and make it bigger. But here we are trying to get the dislocations together and make it bigger dislocation, pile up, multiplication, and this forest thing, cellular structure. So when a lot of dislocations has been piled up, they will make the cellular grain structures. But at the same time, because of this pile up, we need to move these dislocations. There our motive was something different, to lock the dislocation movement, but here we want the dislocation to move, and also at the same time we want the dislocation to move faster to get piled up. So cross slip is one phenomena which is really needed for this type of cold working strain hardening. So cross slip, what happens is, if there are a lot of planes like this one, and each plane is separated by another plane distance, and if this plane is having such some kind of pile up of the dislocation, this plane is having some direction, some slip direction, the another plane is also having some slip direction, and you can see all these planes are similar. The coordinate of all these planes are same because they are parallel to each other. And if all the planes are having the same slip direction, slip plane or slip system, then this dislocation, piled up dislocation, will try to move forward. So what happens is, if there are some planes, this dislocation was previously here, but now it will try to move forward. So what happens, after some time, this dislocation will come to this plane, and now it's in this plane only, not in this plane. This is in, this is plane 1 2 3. Previously it was only at plane 1. Now it has crossed the variant and it has come down to plane number 3, and this is how it moves. And this phenomena is called cross slip. For screw dislocations, they move along the Berger vector, and because the movement of the dislocation and the direction of Berger vector is parallel to each other. So this is why cross slip in case of screw dislocation is easier. They very easily can cross slip from one plane to another plane because all the planes are parallel and their Berger vector is also parallel to their movement. But for edge dislocations, their movement and the Berger vector is perpendicular. So they need to find another slip plane which is having the same direction like their dislocation movement, then only they can cross slip. So this is why it's just leaping from one plane to another plane. It's moving, it's looking like that. But for edge dislocations, it's like climbing, jumping from one plane to another plane because they cannot cross slip. They are not having the preferable Berger vector direction and the slip direction. So for edge dislocation, those are called climbing. For screw dislocation, these are called cross slip. And both this type of cross slip and climbing is needed for us this time because we really want to move the dislocations, because we know the dislocation density is so high that even if we allow the dislocations to move forward in a particular lattice, it will lock themselves after some time because of their own nature, their own nature of getting or finding a low energy gradient, energy configuration uh, low energy configurations. So this is why cross slip is important. Also, for higher SFE, which is stacking fault energy, the cross slip is easier. So if the width is minimum, so stacking fault means there were previously one dislocation, but now somehow because of the external load, the dislocation has been divided into two parts, and this position in between two dislocation is a favorable position for the solute atoms to sit. But this solute atom can sit if the position is vacant and the position is favorable for the solute atoms. If this vacancy or the distance between these two stacking or divided dislocation is not that much that a solid atom can come and sit over there, then it will not be a preferable site for the solid atoms to come and sit. So in that case, the stacking fault energy will be higher, and nobody wants to come and sit in a higher energy state. They always try to go in a lower energy state. So this is why this stacking fault energy can be overcome for the dislocations, and they can move easily. They can cross slip very easily. So if there is a pile up of dislocation and in between them some stacking fault has happened, they can overcome the barrier of the stacking fault very easily if the stacking fault energy is high, and the so that means the stacking fault width is lower. So is it okay for you?
Ma'am, I have one question here.
Yes, yes.
If take example, we have a lower staking fault energy. First, ma'am, staking fault energy is a property of a material. Can we say like this?
Property of a not material property, not a property, it's a characteristics of that solute and dislocation movement, their
Okay,
interaction.
okay. It depends on the particular plane. Means I think.
Yes, it depends upon how the solute atoms are, what is the property of the solute atoms, how much hard they are, and how much consistent the dislocations are, how much cold working we are giving or we are applying, and how the solutes are interacting with the dislocation in case of heat treatable. So
Okay,
how the dislocations are moving, how they are facing the cold working, this type of things.
okay. So, ma'am, if we have a lower staking fault energy, so let us take example. We have a two plane, one plane having higher staking fault energy and another one having lower staking fault energy. So, in which plane the generation of the dislocation is easy?
Okay, so dislocation to move is easy for the higher stacking fault energy region.
So,
So
ma'am, moment of the dislocation and generation of the dislocation, is it different or same?
movement of the okay, uh, generation of dislocations doesn't matter on the material. If it matters how much cold working you're applying. Stacking fault is the result of the dislocation movement only. So if there is, so first at first place the material is at step 1, so we are having a proper non-deformed material, so it's having no deformation, so it's having no dislocations. There is no chance of the stacking faults because stacking fault is a result of the dislocation movement and the breaking or dividing the dislocation from the middle.
And how it depends on the dislocation core size? Can you relate SAP
Okay, so
with
let's
dislocation
see.
core
So
size?
at first step, there is no dislocation inside the material. Okay. So
Right.
after deforming means after I am pulling the material, I am giving some external force. The material did not sustain that load and it has deformed. So there are now few dislocations, some new bond dislocations. Now if the length of the dislocation is very high and in between the solute atom is coming and interacting with the dislocation, trying to catch up the dislocations, and also at the same time we are still pulling the material, giving the external force, it may happen the dislocation has now been divided into two parts, two ordinary dislocation, and the in between portion of this two is can be a preferable site for the solute atoms to come and sit, because the energy of this portion will be lower, and also there is a particular lattice structure of the parent metal and there is a separate lattice structure of the solute atoms. So solid atoms find it difficult to find, or they feel difficult to find a vacant place in the parent lattice and jump in that and sit over that. But as this is a new phenomena taking place inside the material, this dividing the dislocation into two parts, so in between place is somewhat different than the parent metal. The situation and environment of this portion in between two dislocation is now somewhat different than the parent metal environment. So the solute atoms feel a preferable site to come and sit over there. But for that, the spacing between this two dislocation needs to be uh, needs to have a certain value so that the solute can come and sit. Obviously, if it happens like due to some reason there is a stack, so this is called the stacking fault. Okay, and the energy associated with this place is called the stacking fault energy. Now if somehow the stacking fault has occurred, but the distance between two ordinate dislocation is not that much that the solid atom can come and sit over there, means there is a high energy in that stacking fault. The energy is high. Why? Because this two dislocation will always try to again catch up themselves to get their original shape and size. This is why the energy is high. So at that place, if the cross slipping is happening inside a particular plane, so in that plane the cross slip is happening or taking place, then if this stacking fault is having higher energy, then it will have the tendency to get attached again and make the original shape and size and geometry of the dislocations. So this is why for cross slip, stacking fault energy needs to be higher. But for heat treatable alloy, we always want the stacking fault energy to be lower to so that this can be a preferable site for the solid atoms and to come and sit over there. So is it understandable? Did you get anything?
Yes, understood, ma'am.
Okay.
Right.
If you have any other doubt, you can ask.
Ma'am, what do you mean by dislocation core size means? It depends on the number of
How much?
dislocations or dislocation density present in a lattice.
Dislocation size means
Di-
the extra half plane size. Okay, it's not exactly the extra half plane size, but also how the dislocation is moving, in which direction, how it's behaving, and pile up things. If we are talking about the dimension of the piled up things, means there are a lot of dislocations piled up at a particular place. I have demonstrated the picture now. It's a black portion like this, so there are, you can say, thousands, millions of dislocations placing over there. This is why it's looking like a black portion under microscope. Otherwise, you can imagine dislocation is made up of few atoms only. You really can't see the few atoms under a microscope. Is it okay?
Yeah, yes, ma'am. So, when we generally use this word dislocation core size, so actually I'm not able to understand that this course dislocation core size means the length of the dislocation is more or the density of the
Dislocation core
dislocation is
size
more.
means the size of the, if this is the dislocation piled up and it's moving in this direction, so this will be the core size. How, in which direction it's moving, that much portion dimension,
Okay,
the
okay,
maximum possible.
okay, ma'am.
Okay. And also, okay, so this was the concept of cross slip uh, climbing. Climbing is used for age, and cross slip, this word is used for the screw dislocation. And also the dislocations need to have a common sleeve direction to move for screw dislocation. But as the screw is having the parallel Berger vector or the Berger vector parallel to their own movement, a direction of their movement. So it's easy for them to cross slip unless until there is no such hindered thing in between them like lower SFE or something. So these are some favorable conditions for the dislocations to move, because for cold water,
Um,
yes.
Sorry to interrupt, ma'am.
Sure.
Ma'am, like in many books, it is written that the velocity of edge dislocations is greater than the velocity of screw dislocation. So, like, is this
Yes.
statement
Okay,
true?
okay. No, no. It's true. The velocity of edge dislocation is higher always, because the screw dislocation moves like the helical or along the helical path. If you see how I cannot draw the things here, but if you can go through any picture available in Google, you can see there the movement of the screw is typically different and tougher than the edge dislocation movement. So this is how edge dislocation can easily move. But for this cross slip, I am telling you that it's easy for the screw to cross slip than a edge dislocation to climb. There is a pile up of dislocation. It's not a single dislocation. For single
Ma'am,
dislocation,
because if we see in terms of distortion,
yes,
no, not exactly in terms of distortion, but the energy of the edge dislocation, then like energy of edge dislocation is greater than the energy of a
yes,
screw
yes,
dislocation.
yes.
Is it like that, ma'am? Because we know that every system wants to minimize its potential energy.
Yes.
So, like the density of screw dislocations will be greater than the density of edge dislocation, as the screw dislocation distorts less.
uh, you can say like for age dislocation, if the energy is higher, you are saying, then it will be uh, it is a normal thing that age dislocation will move faster. It will uh, try to get a low energy configuration, and it will try to move and reach a low energy gradient portion in the lattice faster in a rapid way than a screw dislocation, because of their easy movement and the energy and all those things. But when we are talking about the dislocation pile up, for pile up, for pile up, uh, what I'm trying to say is, this is one situation that is favorable. This one, that low stacking fall energy. So when we were talking about the movement of the dislocation, I didn't say that these things are some conditions for the dislocations to move, because there was one dislocation though that can move very easily. But here a lot of dislocation has been piled up at one place. There are some other two types of dislocations, and there are they are having opposite signs also. So there, due to a lot of dislocation and the more dislocation density, it will have different condition for them. It needs different condition to move. For dislocation, there is no condition to move inside the material. Only if you stress, the dislocation will move. But for dislocation pile up, it needs another condition and some more properties, or some extra, some different situation to move forward. So that particular favorable situation is this cross slipping of the screw dislocations. And it's easy for the screw piled up dislocations to cross slip because of their Berger vector. It's not like screw dislocation will always feel easy to move forward. It's easy for the edge to move, but for piled up, it's vice versa because of that Berger vector thing. So, is it okay, or others I can do what I can do in next class? I'll show some video or photo
Yeah,
if I
that
can
means
get.
like that velocity concept I can visualize now.
Okay. So you have to visualize, because these things I really cannot find a photo or proper video to show you. It's only you can see under microscope. And also, if you see the grain boundary, grain things, dislocation pile up under microscope also, you will not find the separate things. You cannot distinguish the separate things. What is dislocation pile up? What is grain boundary? If you don't know about it. So, in certain amount, you have to visualize the things, how the dislocations are moving, because you really cannot see the movement of the dislocation. We cannot control or capture those simulations under any such normal microscope. You have to go for very high-end software or something. I don't know, does it exist or not? But yeah. So yeah, for from lecture 4, the new topic was started, that is recovery and recrystallization. So for overaging, we have seen that for heat treatable alloys, we did the strain hardening by aging, by natural aging and artificial aging. And after that, if we keep the material for longer time or for longer temperature, the overaging happens. But for cold working, you are stretching the material and you are doing the strain hardening. But for again, to get back the ductility, you cannot stretch back, right? So for non-heat treatable alloy, it's a problem to get back the ductility. You have to go for other things to get back the ductility. But for heat treatable alloys, it's fine. You can get back the ductility by just normal uh, heat treatment, carrying out for some more time, like the overaging. So for non-heat treatable alloy, what we do is we go for some other techniques like annealing, normalizing, these things. So quenching, these are three most commonly known phenomena. So quenching we have already seen. It's for hardness. To increase the hardness, we do quenching, because quenching is like heating a particular material above the recrystallization temperature, and then we sorry when we cool down the material very fast, very rapidly, by dipping the material in oil or water. But normalizing and annealing is somewhat different than quenching. In annealing normalizing, we get back the ductility to some extent. So we increase the ductility, or in other words, we decrease the hardness. So annealing is like we heat up the material up to certain time, up to certain temperature. It will be always, in most of the cases, it's more than recrystallization temperature, and then uh, we cool it down in the furnace itself. So you can imagine for stainless steel, mild steel or aluminium also, we sometimes do the annealing in 950,000 degrees centigrade, and then we are letting the material cool down inside the furnace. So as soon as the furnace will cool down, then only the material will get cooled down. So for annealing, it takes a day long time. But for normalizing, we keep the material in normal open environment in air. So it's basically an air cooling. We similarly heat up the material up to the recrystallization temperature, and when then we let the material get cooled down under air. So this three are very important. If you are appearing for some interview or going for some test examination, you'll face this type of questions like what is quenching, annealing and normalizing, the difference between three. So in both the cases, we go up to recrystallization temperature or whatever temperature we want, but we cool it down differently. For quenching, it's water or oil cooling, fast cooling. For normalizing, it's slow cooling in the air. In annealing, the slowest cooling in furnace. So there, the recovery and recrystallization happens. So recovery means we are recovering the ductility. We are trying to get back the ductility. And for recrystallization, so what does it mean is, in cold working, we have made a lot of dislocation inside the material, which has now come up with the pile up, the cell structures. So how much or how much density of the dislocation we are having right now in the material, we can imagine. We cannot imagine actually. To get back the ductility, we have to have some dislocations to move inside the material, but we cannot let all the dislocations move at a time, because one thing is we cannot let the dislocations move at a time because the dislocations are piled up. They cannot move freely right now, and also if they move, how much or how many dislocations will move and how many will still be present in the pile of cell structure, we cannot determine. We cannot define those things. So what we do is we separate out this piling up. We let the dislocations be arranged in the pile up configuration only, and we this is how we do the recovery. And recrystallization means we make we do certain things by which some new strain free grains will be nucleated. So there is one concept of nucleation and growth under recrystallization. It's very important. The recrystallization temperature is different for different material. The heat treatment, some well-known heat treatment are H900, H1050, these things. But so did you talk about these things like three digit H something? Like H900 is one type of heat treatment process. Shailesh? Okay.
Yes, actually, ma'am, I talked about the three digit that we have represented the aluminum alloy,
Okay,
like
so
five.
there is one heat treatment which is H900, which we typically do for stainless steel. I don't know whether we do it for aluminum or not,
Okay.
but for stainless steel one is called H900. So what does it mean is we let the material get the nucleation and growth, means the recrystallization, we wait for the recrystallization to happen inside the material. So for that we use H900, but this 900 is Kelvin, but it's not the temperature we typically use for material, because this recrystallization temperature is unique for every material. It's specific to every material. Every material have their own property and characteristics, because of which the recrystallization temperature and time is also important factor. This both are unique for every material. So we are just heating up the material up to certain point below melting point, but above recrystallization temperature. We are keeping or holding the material at that particular time, which is the recrystallization time, and then we are cooling it down. What does the annealing do? And this is how we get some strain free new grains. So what does this strain free new grains mean? Anyone? This line was repeatedly mentioned in last two lectures, lecture 4 and lecture 5. Some strain free new grains have born. What does it mean?
I guess like the grains that were present earlier after cold working were disoriented because of cold working. So instead of them, some new grains were formed which which do not have those sort of strain pressure.
Mm, actually it means
Ma'am,
strain.
actually,
Yes.
okay, yes.
Yes, yes,
Ma'am,
please tell me.
ma'am, actually, the two grains are equivalences. Like if there is some grain boundary between the grains, means there is two grains, and in between there is a grain boundary, and there is some misorientation of the these boundary of these two grains. Then, if after rotation, means after lattice rotation, if these grain boundaries are completely matched with each other, then this nucleation will start. Means before that it was a strain, but after after making a bigger grain, after merging together, it becomes a strain free. Means there is no grain boundary between them.
Uh, okay. What you have told me is correct. This is how the nucleations take place. But no, it doesn't mean it doesn't answer my question of the strain free grain. So strain free grain typically means there is no dislocation in the particular grain. Strain is a word which is always associated with the dislocations. Strain free means it there is a grain which is having a particular grain lattice. uh, the lattices inside the grain is arranged in a particular direction inside a grain, and in all the lattices inside that particular grain there is no mismatch or there is no dislocation. Grain means, so it's an unit cell. By combining all the unit cell we have a lattice, and how the unit cell is present, the grain will have that direction. So this is one grain and it's having the direction like this, all are arranged in this manner. It can happen like all the lattices are arranged in this manner, so the grain will have a direction like this, and the material you see under microscope have this type of grains. These are the grain boundaries. First was the unit cell, then the lattice, then the grain, and then the material. And these grains are having some direction. If these directions are in one way only, then it will be called an isotropic or anisotropic. Those are separate things. But this is what grains mean. And if I'm talking about this particular grain, which I have shown here, so this particular grain does not contain any dislocations. All the lattice, all the unit cells inside the lattice is properly arranged, and there is no extra half plane inside the that lattice. And by this type of lattices are there connecting to each other, bonded with each other, and this is how this grain is formed. Now you understand
Uh,
what does this strain free? Yes.
Ma'am, thank you so much for this explanation. It was so nice. But I would like to ask one question, like the direction of means the arrangement of the lattice.
Yes.
Direction of arrangement of the lattice depends on means I mean to
We
ask.
cannot
Uh,
define
no,
how
ma'am.
what
Yes, yes.
on what it depends.
Ma'am,
It's like
yes.
their
The
direction.
orientation of the grain boundary depend on the arrangement of the lattice in a grain, right?
Yes, yes. And how they will be how they will be oriented, we cannot say, because yes, if there is a particular cold working which has been provided to the material, then they will have the grain will have a particular direction, all the grain will be oriented in similar way. But otherwise, if I am taking one material and I am going for the heat treatment or cold walking, there will be no such defined things like the grains will be oriented in this manner only. As I have shown in this picture now, the grains can be oriented in different directions, but when we go for, then this is the material, okay? And when we are going for the cold working, then all the grains will be arranged in one orientation. Is it okay?
And ma'am, can we have a different orientation of lattice inside the grain?
Can we have different orientation of lattice inside a grain?
Yes, because
uh,
a grain is made up of the arrangement of the
yes.
lattice.
So
So can we have a different orientation?
how the lattices are oriented, this is how we define the grain. So if this is one grain and this is another grain, how this grain is made, like up to this portion the lattices were oriented in this manner, and beyond this portion the lattices are oriented in this manner, and at the grain boundary there is one dislocation, we can say this is how the grains were separated.
Understood, ma'am.
Yes.
Thank you. Yes,
Okay.
all right, ma'am.
So this was very important to know. First, what does this strain free grains mean? So I think we can stop our discussion here. We'll go or we'll jump into the previous year questions. We'll discuss the questions. Then from next class, we'll start again from this recovery and recrystallization, because the time is already 7:40. So there are some effect of decrystallization and all. I'll continue in the next class that thing. Let's see the assignment. Okay. So the current year assignment, it's, so I'll go, let's do one thing. Just see the previous year assignment. Yes, this is the previous year assignment for week 5. So this is for your practice purpose only. I'm showing. So the first question is, non-heat treatable aluminum alloys are usually strengthened through. I want you guys to answer.
Answer is strain hardening.
Yes, because the aging thing cannot take place in the non-heat treatable alloy, because aging is a kind of heat treatment, right? So yes, strain hardening. Next is aluminum alloys in the annealed condition are designated by temper. The
Temper
nomenclature,
O.
nomenclature has already been discussed. Okay. So the next is addition of Cu or copper in 7000 series aluminum alloy. What? What is the answer? What is the answer? Anyone? Just let's have a try now.
I guess increases the corrosion cracking resistance. Yeah, and so
Huh.
about the solvent temperature, I guess it should decrease, no?
What does this solver's temperature means?
Like for the GP zone, like the solvent temperature on addition of copper decreases.
You are saying that this answer should be right along with the second one.
Yeah, like I was asking about the third point correct or not. Like I thought
Huh.
it's otherwise.
Okay, so what is your explanation behind this? Why it should
Uh,
be?
I thought that I heard that this happens like copper addition of copper like affects the GP zone solvent temperature. So I wanted to confirm
Okay,
this.
so what is solver's temperature? First, tell me. Any idea?
It's like that temperature in the curve that we see, and the place where that was triple S is stable.
Hmm. Yes. So, okay, no problem. We'll see. I'll check whether it's right or not. You are right. What is solver's temperature? So, I'll see whether it was said in the lecture or not. Okay. Question number 2.
Sure, ma'am. Thank you.
Yeah. Uh, the next question is, which of the following elements are responsible for the formation of S and S prime precipitates? So it's copper and magnesium. Okay. Okay, so this answer is also correct. I didn't notice. You have got your answer, right?
Yes, ma'am.
Okay, this one is also correct. Increase the thermal resistance of the GP zone. Yes, obviously the resistance to corrosion cracking, stress corrosion cracking is increases. and the thermal resistance of the GP zone will also increase because the solver's temperature is now increased. So there will be some more time where up to which the SSS or the what's it, that thing will be stable. Beyond that, this GP zone formation will happen. So there is a resistance to the GP zone formation. There will it will have more time. Uh, it will get more time to start the formation of GP zones. So yeah, it's always also correct. Next is, what does the meaning of H18 temper in the aluminum alloy? It's pretty easy.
It is fully strain hardened.
Yes. So next is second digit in the H24 temper designation of the aluminum alloy is referred as.
The
It
first
is,
one,
yeah.
Degree of strain hardening remaining after annealing treatment. So the next question is, which of the following aluminum alloy is used to make fuselage in aircraft?
the last one.
7050.
Yes, it's used. Then the small amount of chromium is usually added in 6000 series aluminum alloy to
I guess increase the machinability and reduce the current sensitivity. Okay.
inhibit. Okay, chromium is always added to inhibit the grain growth. This is one thing, and refine the grain size. In other alloys also you'd see chromium is added for the refined grain size. It has that characteristics. Okay, I have another thing to say. Um, Whenever one alloy is used for a particular application, always remember this. Just for example, in aircrafts, in aerospace industry, there are lots of parts in a particular aircraft or a rocket. So in rocket, somehow, suppose this AA707 7050 is used, but it's not true that this 7050 will be used for T6 condition or T7 condition only. It is possible that when this 7075 is used for the fuselage to make the fuselage of the aircraft, it will have the temper of 707 T6 condition to have the peak hardness. But at the same time, this 7050 is used in an optomechanical component where it needs to sustain very high frequency movement and also the rigidity. There we are making it with T7 condition, or the vice versa. We are using the T6 condition for the optomechanical components because obviously it needs to sustain very high frequency movement and a very rough condition with a great rigidity. For the same alloy, I'm using it for the making of the aircraft body. There we can use it for 77 condition because T7 is overaged, so that is having some ductility at the same time with a lot of hardness. So it's possible. And yeah, this alloys are used at different heat treatment condition for different application in a same product, in a same product. So the next is strengthening of aluminum lithium alloy takes place mainly due to the formation of what?
This is ordered precipitates.
What would be the appropriate aging temperature for aluminum, magnesium, silicon alloy?
170 to 200.
So this were the okay, yeah, that I was thinking of. APB is also true for strengthening now because ordered precipitates is somehow also related to APB. Yeah, it's also a correct answer. So yeah, these were the questions. I have some PPT also, some material. I'll show you. So this is one thing I prepared for you. So cross slip is the movement of the screw dislocation from one slip plane to another due to the local stress. So obviously stress is something which is associated with the energy as well. So depending upon that and also in which direction I am applying the cold working, the slip will take place, or the movement of the piled up dislocation will take place. This is an example of the screw dislocation, how it's moving from one slip plane to another slip plane very easily because of its parallel Berger vector. In the next point, it's written the Berger vector and slip direction is parallel in case of screw. This is why there are infinite number of possibilities in which it can move through the cross slip phenomena. Then for higher SFE or stacking fault energy, cross slip can occur very easily because of that small width and not preferable situation or environment for the solids to sit, and also lower stacking fault width gives rise to higher SFE, which is like lesser strengthening. Means we are not okay, lesser strengthening we are calling it here, because normally what happens, lower SF or lower stacking fault width will have higher SFE, so it will have a tendency to get attached, tendency for the dislocations to get attached again, means they will again look or work like one dislocation, and they can easily move. So for normal condition, for heat treatable alloys or for an alloy at normal condition, it's it will give rise to less strengthening or ductility for the movement of dislocation or due to the movement of dislocation. But for our case, non-heat treatable alloy and lot of cold working, this lower SF with and higher SFE will give rise to higher strain hardening because of all the things we have discussed today. So good recovery. So recovery we'll see in the next class. What does it mean? And as I said, climb is the movement of the edge dislocation from one slip plate to another due to the local stress. Uh, yeah, so this much I think it's more than enough for today's session.
Excuse me, ma'am.
Yes, yes, please.
Actually, in heat treatable alloys, the moment of the dislocation because of the low width of a stacking fault,
Hmm.
so there is easy moment of dislocation will decrease the ductility. Means, will it
No,
decrease the ductility,
okay.
ma'am?
So let me draw. If that is a ductile material like aluminium, we are applying some force, the dislocation is moving. If there is a stacking fault, the width is small, means the solute atoms cannot sit and it is having much more stress or energy, or it is having a tendency to get attached again. So there it will get attached again. It will look like, or it will act like again one dislocation, and it can move easily again. It will give rise to the ductility. It will result the ductility or ductility property. But if the stacking fault width is more, the solute atom will sit and the strengthening will take place. Okay. But in our case, for cross slipping, we want the dislocation to move and get piled up. So for that case, we don't want this stacking fault width to be much more. We want this to be little so that the SFE will be high, and we can go for the strain hardening for non-heat treatable alloys. So this stacking fault phenomena is a bit different and opposite for both the cases, for heat treatable and non-heat treatable alloys. Is it okay, or do you have any?
Understood, ma'am. Understood.
Okay.
Ma'am, I have one question.
Yes.
I think to join this course, as per my research work, it was
Okay.
means I thought it is very helpful, and I think it is doing the same. But ma'am, actually, I am working with. Can I ask one question related to my research work?
Yes, yes, please. If I can
Oh,
answer, I'll.
okay, right. Actually, I am working with the friction stir welding of aluminium alloy, and uh, actually, I am not able to means select which type of alloys I need to use, like heat treatable or non-heat treatable alloys. But I start studying all these alloys about these properties and all. But ma'am, actually, could you please suggest me? Uh, the aluminium alloys that have some less work that has been done on that alloys, and that I need to proceed further with that, and I need to look the
So,
research paper over that.
you want a preferable aluminum alloy that will be good to go with the friction star welding, or you want some aluminum alloy which has not been uh,
No, that is good for friction stir welding, and that has not been used in like till now in research
okay.
mode. Means that I can
So
proceed
I
for.
can say the heat treatable alloys like 6000, 7000 series is the hot topic in research right now in friction stir welding or normal welding, laser welding, additive manufacturing. But not heat non-heat treatable alloys are challenging because it needs the cold working. We really cannot play with the solid atoms or alloying element. So we basically mix the alloying element to get the hardness. We are getting some hardness because of the solute atoms present inside the non-heat treatable alloys, but we cannot play further with that solute atoms so that we can increase the hardness without mixing more solutes. So for that reason also, non-heat treatable alloys are not been worked really in case of this welding and 3D printing processes. So I can say if you are going with the 5000 series, you can go. Otherwise, I have not gone through the literature review of this aluminum alloys or all type of alloys. I can say for 6000 and 7000 series only that a lot of work is going on. But what other works are going on other non-heat treatable alloys or even with 2000 or 8000 series, I don't have that much idea.
Ma'am, actually, if I want to join like second series or five series together, and one is heat treatable and another one is non-heat treatable, and that too with
Yes,
the friction, that
that
too
will
with
be a
the
great
stirring
idea.
process,
You
means there
can,
is a diffusion. So
yeah.
can it be feasible? And ma'am, there is one question after that. How can we decide that means the particular copper will be means will be diffused with the aluminium, or the zinc will be diffused with the aluminium, or there will be zinc aluminium or zinc copper bond if we go for dissimilar metals, like second series or 7 series. Means in second series we have aluminium copper,
Yes.
and in 7 series we have aluminium zinc. So
Yes.
in both of these the different alloying elements are there. So how can we decide that these atoms can diffuse properly like that? Means, can we have any method?
So, one thing I can say, I'm also a research scholar. So, one thing is literature review, proper bonding, debonding, how it's going on inside the lattice or inside the atoms, you can find in the literature only. Otherwise, it's difficult to say because if it's not been worked yet, then this can be a good research opportunity for you to go with this two types of non-heat treatable and heat treatable alloy and then join it. You can go for simulation first, the online softwares which are available for the simulation, but I don't think the simulation can give you very good result because these things are not feasible to say by simulation how the bonding will take place between copper and zinc. This can be only experimented and see what is happening. You cannot say anything about this that what will be happening inside the material when you'll be doing the friction stir welding. You can only be experimenting. experimenting and say.
And ma'am, can we have a good bonding between the same heat treatable alloys like second series or
Yeah, people are working with 6000 and 7000 series. They are trying to, yeah, obviously the things are not very easy because the alloying elements are different in both the cases. So they are trying different processes to get an optimum bonding between them. I have seen some research works going on where trying to fix 7000 series with 6000 filler rod, but it's a good scope of research. I won't say you should go with this, but you can go with this if you find any relevant research work in this. You have to
ma'am?
find the
Uh,
literature review.
Okay, ma'am, one last question.
Yes, yes.
If the tool is rotating, like take example, if I have taken 5 series alloys and if we have a rotating tool, and if we are making some grooves and we are adding some powder like graphene or
Yes.
some reinforcement I am doing, and over that I am just my rotating the tool along the trans along the well direction.
Hmm.
So in that case, I think is there is a diffusion bond only means is there is a chance of recrystallization means because I am not going with recrystallization temperature.
Recrystallization also depends upon the prior cold working that you have given to it. For
No,
this
ma'am.
case,
Actually,
for
I
yeah,
have not given.
so here you are using powder. So there
Yes,
also you are forcing it to join together, but it
yes.
will not be considered as a cold working because you are powder. Anyhow, it's not possible to give the cold working to the powder particles. And also recrystallization depends upon the temperature and time. Uh, Specific temperature is always there for specific material and it's pretty high. For friction stir welding, temperature will be risen, but it will not be that much like we get typically in laser welding or normal arc welding. So I can't say that yes, there will be some diffusion or there will be the bond. That is the
Uh,
scope of research.
okay, ma'am. Actually, I have seen in some of the literature that they have written dynamic recrystallization
Yes,
during this
there is
process.
another topic, dynamic crystallization, that we are providing or we are attaining the recrystallization without that much temperature. We'll be talking about that, but I don't think that we can say like
Okay,
yes, this will happen. This is a scope of research. This is why you have taken the topic, right? If you can
okay.
say that yes, there will be bonding, that is pretty good, it will be the result, then that will not be a scope of research in your PhD.
Actually, we can increase the strength also by increasing the dislocation density. That means,
Yes.
I think if we are using some powder between by making groove, and if we are just putting my tool over there and we are welding, so I think we are giving some cold work during the welding process. Can I
Yes,
say like
that's
this?
why I told you that even if the tool is rotating, we cannot say that the cold working is taking place
O-
because we are providing the force. We are rotating the tool for the proper diffusion bonding between the powders, but still the amount of cold working that we are giving by this tool rotation, you can't define that for
Okay,
the
ma'am.
powder particles.
Yes, ma'am. I am just coming to my point. So, one paper I got that they said that I increase the dislocation density by giving this type of fold work while rotating the tool over the workpiece, right? So, can I justify this statement by using any micro structural, I means by any micro characterization techniques? Means what kind of characterization techniques that reveals this type of phenomena?
Uh, can you repeat your question? What type of characterization is needed for what?
What type of characterization is needed to just define the dislocation density, preferably in a material. Like if
There is
I am
one thing is FTIR. People go for FTIR to see the microstructural, means micro scale things. Other than that, I think TEM, but I don't think TEM can result in that much accuracy, but I
Yeah,
have to check that.
exactly, ma'am. One of the paper came into picture, I think in 2023 from one of the scholar in IIT Roorkee. So they have used a TEM, means
Okay.
transmission electron microscopy, and they said that the dislocation density has been increased.
In consequent lectures also you'll see that sir has also recommended that TEM can be one process by which you can see those things, dislocations. But I don't know for your case what will be the result and how it will look like. It's okay if you can find any related research work available in Google so that you can have a idea at least where the non-heat treatable alloys are joined with heat treatable, or this type of powder fiction stir was carried out. Other than that, if you want to go for a new research, you're always welcome. What should I say? Your voice is not coming in. Okay, Silesh, your voice is okay. He has left. Okay, so Vanshika, you have no doubt, then we can stop.
Yes, ma'am, it's clear. Thank you.